So the topic of my talk will be going even further on this in the deep connection between the structure of the landscape, and in this sense I will be maybe pushing more in the direction of saying how important this structure might be also in the situation of escaping from the equator, in a couple of examples in which we can play with that. And of course, the idea will be to connect this structure to performances of gradient descent-based method, and this will be realized mainly in this hard inference problem, which is Tensor PCA, and a couple of generalizations that has been already introduced. Before going into, again, a rapid redefinition of the models, I want to give you a little bit of a background. So why are we so interested in gradient descent? Well, of course, because it is a method, an algorithmic approach that is widely used in this convex, high-dimensional non-convex optimization, and a great example is given by the very successful use of stochastic gradient descent for machine learning. And the reason for which, this is such an useful algorithm is that it is very simple. As you can see from these two equations, you have that this is a local method, straightforwardly connected with the empirical risk function, and therefore is very practical. So you can apply it in a very different, huge number of different situations. On the flip side, there is a problem, because when non-convex means full of minima, you already understand that the presence of, the fact that it's driven by the presence of the gradient itself, this algorithm will be problematic, because the algorithm will get rapidly stuck in one of the minima. And this is like a problem that we can anticipate since the beginning. And this problem is thought to be very relevant and very problematic for a class of inference problem. Here you have a maybe non-complete list of them, like planted clicks, ranging up to tensor decomposition, factorization, or completion, in which it is expected that gradient descent will fail badly in retrieving the signal, specifically because of, this is what the intuition will tell you, because of the presence of this large number of trapping minima that would very soon trap your dynamics and in a spurious minimum. Luckily, for this kind of problem, there has been the development of alternative approaches, other algorithms. And however, also for those algorithms, as it has been already introduced by Lenka and Gerard today, it exists a hard phase. So this region of the parameters in which, even if it is information theoretically possible to retrieve the information, for even those better optimized algorithms, it is still very hard, meaning that it needs time that is growing exponentially with the number of parameters to be optimized. And the interesting thing is that it seems that all these algorithms are failing in the same region. So it seems like there is some sort of a rising of a well-defined art phase whose origin and definition is a little bit of a problem, because this different algorithm has been defined and obtained by starting from different setting. So it's very hard to develop a unified picture. So what is the plan here? The plan is the one of coming back to this badly performing gradient descent-based method and understand the details of the connection between these performances and the structure of the landscape, because these are the best candidates for being connected with the structure of the landscape. And once we have obtained the details of this connection, what we can do is to exploit this connection to improve the performances of gradient descent, and maybe try to match performances of better algorithms, or algorithms that have been developed to perform from start better than gradient descent. So that's a challenge here. Can gradient descent be improved so to match these performances? And if it is the case, if we are successful in that, now we could ask the question on how can we interpret this well-defined hard phase now that if gradient descent will be able, this will become the hard phase for gradient descent as well. Is that possible to give a definition of that in terms of the landscape structure itself? So that's the plan. And I have listed a number of problems. And it will be interesting to apply this whole program to this different setting. What we have done so far is to apply this program to Tensor PCA. So this is the slide for the definition. I will really go quickly on that. We have this rank 1 tensor, the corrupting noise, and the observation. You have the variance of the corrupting noise. And the problem is the one of finding the signal starting from the observation. The traditional strategy is the one of using a Bayesian approach, meaning evaluating the distribution of this candidate for an estimate of the vector v by knowing the observation, and this is the posterior, and in which you can recognize the likelihood here. And the interesting part, as Gerard was pointing out, is that a couple of line computation shows that this expression is equivalent to the Boltzmann distribution for a problem that has been already studied in the context of physics. It's a generalization of a spin glass problem in which you have a first term, which is this original p-spin model, in which the couplings are connected with the corrupting noise in our inference problem. And then there is this additional nonlinear field that is originated by the presence of the noise. And there is the signal-to-noise ratio here that I call R instead of lambda. Sorry. An alternative approach, inference approach, would be the maximum likelihood estimate that would correspond of solving the same statistical mechanics problem at 0 temperature, or otherwise minimizing this Hamiltonian. Now, so this is for the formulation of the problem. From the point of view of sampling, from the point of view of retrieving the information, the standard approach is the one that has been developed and is very successful, is the one of using approximate message passing to sample this posterior distribution. But another algorithm that we can think of using is the one that is borrowed from physics literature, which is Langevin dynamics, which is defined precisely to sample this, the Boltzmann distribution in the correct way, and the gradient flow, which would be the 0 temperature version as an algorithm, a gradient descent-based algorithm that would retrieve the information or not, depending on the situation. Going on rapidly on the other definition, to refresh minds, generalized tensor PCA would be this non-trivial generalization of this original problem in which we allow the two different polynomials to be characterized by different degrees. And the connection with the inference problem in this case is a little bit more involved. And while this mixed matrix tensor PCA, which is instead a problem that has straightforward connection with an inference problem, and so from the statistical physics formulation, that would be associated with the sum of two Hamiltonians, P2, K2, P3, K3, when P and K, of course, are the degree of the two terms. So two pure tensor PCA problem summed, put it together. And this is originated by the fact that you can observe either, your rank 1 matrix or tensor corrupted by two noises with two different variances. So you have two sources of information to retrieve your signal. So this is the mixed matrix tensor PCA. And I'm going through all of this because we are using all of this model to understand this connection between landscape and dynamics. Now, for all of them, we will be playing with this signal-to-noise ratio or more than one signal-to-noise ratio, for example, in the case of matrix tensor PCA. And in all cases, this will be connected with the inverse of the variance of the noise. For all of them, we will be searching for a vector on the sphere, because we are interested in the direction of the vector, and in particular we'll be checking whether we retrieve the information about the signal by looking at the scalar product of the vector we have obtained by our minimization or sampling methods, and this would be corresponding to the latitude of the sphere in the case in which the signal is corresponding to the North Pole. Now this, again, a warning, is a very small dimensional representation of a high dimensional problem. So the warning is that the equator here is containing the majority of space, as Gerard has discussed, and the idea is that there will be a big entropic issue in escaping from such an equator, but on top of this, we will be considering the structure of the landscape at all the different values of the latitude to understand whether this plays also a role and to which extent, and how to deal with that, how to improve on gradient descent to avoid to be trapped. Okay, so the first chapter of this analysis goes through the study of the risk landscape at the different level of the latitudes. Please.
So choice of V is random, right?
Yes. So as Gerard said, this problem is in principle invariant under rotation. So I can just define to put my vector in that direction, and this will break the invariance for that particular problem, but I could choose any other, and this doesn't change. Okay. So every time I choose any vector, then I rotate my sphere so that it goes in the North Pole, and the equator and the latitude will follow as definition.
Try different vectors.
Sorry.
You try different vectors, or you don't?
There is no need.
There is no need because of being there.
Because it's just invariant. Yes. Right. Please.
Actually, why V is not aligned? Why V is not on the equator as well?
Well. Yeah, I mean,
it's randomly chosen, so
it is randomly chosen. But the thing is that, so the equator is defined as everything that is perpendicular to V, okay, which is the rest of the space.
So this means that between two randomly chosen vectors, I can always draw this kind of picture, right? Where there is,
if you had two spikes, then you would have one in one direction because you choose to put one in the North Pole. The second will be definitely on the equator, okay? But if you have only one, you can always put it on the North Pole, and then every other initialization for your algorithm will start from the equator.
So the equator is just orthogonal space?
Yes, it's the orthogonal to the vector.
And if you had two spikes, you would have an equator of dimension one less, but it would be the entropy problem would be the same.
Okay. So how is the risk landscape? Let's try to give an answer to this question. Well, a lot has been already anticipated by Gerard. The tool we are going to use is this Katz-Rice formula. That would be...
That's one question, the previous slide.
So, sure.
So I guess the intuition is, again, in high dimensions, you know, the whole volume is on the equator, right? Mm-hmm. So does having an extra dimension help? Because you want to go, if you had V, which was one dimension higher, then there's a chance that you can escape the volume, because now the volume becomes a shell in the higher n+1 dimension. That doesn't.
No, it's
not at all. Okay.
The right way to picture this is imagine an immense flat landscape with two tiny holes. And that's the equation.
If you added dimension, I think you would make things even worse.
Worse, you're saying.
Because the problem is precisely the big number of dimensions here. Okay, so rough landscape. How do we get the details of its structure? We use the Katz-Rice formula. Here you have like the formula, the starting point for the computation, and I wanted to show you that because I want to underline that we are searching from this stationary point or critical point of our landscape that correspond to a certain value of the risk function and that correspond to a specific value of the latitude. Okay. Now, for a general problem, it has been shown by Subag that the annealed computation is luckily very good already. I mean, it's giving the exact result for this specific problem which you have the p-spin model, for example. So it's already doing the job. However, in this case, we have to do the take the additional complication, which is the one of evaluating the typical number of critical points by taking the average of the log, meaning doing the quench the computation, because we want to focus on the stationary points that are at each level of the latitude. And for this computation, this really makes the difference at the level of the result. So to evaluate this typical number of points, we have to introduce replicas in the computation, and this makes, well, this becomes a very, well, a formidable task that Valentina was being able to tackle and obtain this structure of the stationary point scanned at all the different slices for the sphere. Now, before going into showing you what is the structure, what does the structure look like, I want to give a further comment, which is the fact that through the computation, we are going also to obtain information about the Hessian evaluated at this stationary point, and in particular, the distribution of the eigenvalues, so the spectrum of this Hessian. And therefore, we're going to have the information about the stability of these stationary points, in particular, if this distribution has a support that is completely positive. This will correspond to having a minimum in our convention, while this figure would represent the situation for a saddle, okay? So what we are going to look at in the next slide is the structure of the minima, meaning the one that are characterized by a distribution of these eigenvalues, which has positive support. And here it is, the whole result. So this is evaluated for this generalized tensor PCA, in which we have different value for P and K, so P plus K. And in particular, we have the linear field in this first figure. And the code here is, so you have a red band in the terms of the latitude. Every time you have a finite range in terms of the risk, that is in which there are a large number, actually an exponentially large number of minima in the landscape. And as you can see, well, this is there for different values of the signal-to-noise ratio here. What you observe for the linear field is that this whole band is moving towards a higher value of the latitude, which means that the problem is easy in some way. As soon as you have a little bit of signal-to-noise ratio, you're pushing this problem up. The whole band up, so it means that you already are having some sort of information. We have other lines here. We have the deepest minimum, which is this solid line here, and the highest minima in the risk function, which are also the most frequent ones. Okay, these are all information that will turn out to be useful in the following. What is important here is that, well, as soon as signal-to-noise ratio is non-zero, for this problem, you will already start to get information about the signal. Things become different for the quadratic field, in which you need a finite signal-to-noise ratio to hit the information theoretic transition, meaning to have that this deepest minimum will contain some information about the signal. But even after that, well, you will have this whole band of minima that probably are going to trap your gradient descent-based dynamics on the equator, not to talk about the entropic problem. And this will give you an algorithmic gap for this kind of algorithm, at least. But for the quadratic field, this algorithmic gap is still finite. Things are even worse, of course, for k larger than 2, actually, so k3 or larger, for which this algorithmic gap becomes infinite. And one thing I want to notice is that these most frequent minima at highest value of the risk function are always staying at the equator for the k equal to 2 and k equal to 3 problem. Okay, again, this will come back later. So this was the structure of the landscape. And then, of course, we could try to speculate on how would it be the dynamics, dynamics that would definitely start from the equator, because if we sample at random, we will definitely start from the equator. And the question is whether we will be able to escape from it. And it seems like a gradient descent based method would always fail in such a situation. So let's see what indeed the dynamics is doing. So let's analyze the result from gradient flow and Langevin dynamics in this setting and compare with the expectation from the structure in the landscape. So this is something that we have done by focusing on this mixed matrix tensor PCA. This problem came out as particularly handy to compare the performances of Langevin dynamics, so this gradient descent-based dynamics, with approximate message passing. And the reason, because we want to the reason for which we wanted to compare with approximate message passing is that, well, this algorithm is proven to be optimal for this specific kind of problem. So we wanted to understand whether gradient descent can become optimal, at least in certain situations. So we performed this study. We solved the dynamics, the Langevin dynamics, in correspondence of the optimal bias setting for this mixed matrix tensor PCA. And here you have the phase diagram as a function of the variances of the two noise. In fact, you have the variance here of the P, so the tensor, and 1 over the variance of the matrix component. And you can distinguish the different phases here. You have the impossible region, so where it is information theoretically impossible to retrieve the signal. And then you have two hard phases, meaning that in this orange region here, both the algorithm, approximate message passing, and Langevin will fail. But then above this line here, approximate message passing will perform well, and Langevin will badly fail. Okay, so Langevin is worse. And then it becomes easy for both of them. Okay, now the situation here is this. Here you have the algorithms, how they are performing as a function of the what is the amount of signal that they are able to retrieve. And the two algorithms are approximate message passing, doing really well since the very few steps, and gradient descent, very, very badly. Okay, and this is at this point here. And the question is, can we improve on that? Okay, and can we use the landscape structure to, or at least what we know about the landscape structure, to do better than that? Now, the idea is that we can, and we can because we know what is the different behavior for a quadratic field and a cubic field. You remember, the quadratic field was less bad, especially at the equator, because it was associated with an algorithmic transition of order 1 in terms of the signal-to-noise ratio. So one strategy that we thought of would be the one of getting rid of the information that comes from the tensor. Okay? So we just erase that at the beginning of the dynamics. And we use only the metrics component to escape from the equator. And then what we do is to reintroduce the tensor with a certain speed to retrieve the entire information at the end of the dynamics. And here you see the result of this procedure for different speed of the reintroduction of the tensor. So this is the fastest, this is the slowest. And you see that this works. Okay, so in this case, the knowledge of the landscape has been able to shrink the Langevin hard phase to, well, the limit of the hard phase of A and P. So in this way, gradient descent is able to perform as good as the optimal algorithm. And what is even more striking is that we can do that, and it's performing better, Langevin, if we mismatch the Bayes optimal condition, which is some sort of paradoxical from this Bayes inference perspective. But it's something that has been suggested to us by the landscape. Okay? The downside of this procedure is that, unfortunately, this is very model dependent. I mean, it's very specific to this kind of problem, okay? And what we wanted to look or search for is something that is more general than that. But it's the first result, okay? Now,
this initialization that you have here, you could have just taken the top eigenvector of your matrix part, and it would already have put you in the right direction, right?
Yes, but we are testing gradient descent and saying, checking what is, yes, precisely.
This is why it works, this first phase.
Yes.
Because that's above the transition.
Yes. This is the reason for which it works, and we wanted to check. Yes, we are just seeing whether how gradient descent, which doesn't use this trick, okay, in principle, can find its own way in that direction, okay, and we do that just playing with the landscape structure. Okay, so since the landscape was giving us the good intuition here, one other thing that we could ask is to which extent the landscape can tell us quantitatively where the algorithmic transition for a gradient descent-based method is located in this phase diagram, for example, for this same problem.
Sorry, just to understand, so what you observe is separately noisy matrix and noisy tensor.
Yes.
Correct? Separately. So in the procedure you described, so you first initialize with only matrix measurements, right?
I follow, yes, the
and
gradient.
Then include the mixture. So can you just use the, what happens if you just use the tensor measurements in the second phase?
It's not going to as good. If you use, forget about the metrics, it's not going to be as good because you are getting rid of some of the information that was contained in the, sorry, if you use only the tensor, it's not going to be as good because you're not sampling the posterior that you would do by including the information that is contained also in the metrics. Okay, so we have to, like...
So it's more than just initialization, right?
In this case...
The matrix contribution.
Yes, of course. So it amounts to the total amount of information at the end of the dynamics, but at the beginning of the dynamics, it is the crucial element, the thing that you need to take into account, and actually the tensor part is mostly bothering you, is not helping, even if it in principle contains some component of the signal itself. The noise part is dominating and is messing up the beginning of your dynamics.
And maybe also for understanding, so matrix PCA is optimal, right? You can go all the way to IT, right?
Mm-hmm.
So, but here you're even shifting this, like, but you have additional information right now on tensor, 3 tensor noisy replication, right? So are you saying that you can shift this lambda even like less than 1 for the matrix PCA?
No.
The introduction of this additional?
No, I mean, when I say that the tensor is useful at the end of dynamics means how accurate is going to be the information about your signal at the end of dynamics. In this sense, it's better, but it's not moving the algorithmic transition, okay? I'm not improving on that with the tensor. Okay. So what we did here was to use the information on the landscape to understand what the dynamics is doing. So here we come back to the original problem when we use tensor and metrics at the same time. We only focus on Langevin. Actually, in this particular situation, we focus on gradient descent, so 0 temperature version of the gradient descent-based method. Actually, it's gradient flow because we focus on the continuous version. We have the impossible phase, the gradient flow hard phase, and here we have the algorithmic transition. You can see it. That comes from the study of the dynamics, and while surprisingly, the information that comes from the landscape is mismatching that, okay? What does this line mean? Well, it means that in this region here, there are not minima, okay? Or at least not an exponentially large number of minima, but below that line, there is an exponentially large number of minima in the equator, okay? So it's surprising the fact that you start from the equator, you are dealing with an exponentially large number of minima, still your dynamics is succeeding. And it's very striking, very surprising. So we had to find an explanation for that. What's going on here? So we had to focus, what we did was to focus on the dynamics. And focusing on the dynamics, this is a plot of different dynamics at these different spots here in the figure. This is the risk function as a function of time. And what you see is that all these different dynamics are flattening, are approaching a certain specific level of the risk function. And then at a certain point for these two up here, it is escaping. It is escaping and retrieving the signal, so reaching this lower value, which is the good one. Now, what this figure cannot tell is that when the dynamics is flattening here to this different level of the risk function, the latitude that this dynamics is exploring is still on the equator, okay? So what is this level, okay? By looking at the structure of the landscape, we can recognize that this level of the risk function corresponds to the bottom of this most numerous and high minima in the whole structure of the landscape. So these are the most numerous minima. So it's natural that your gradient flow will be attracted by this minima. And there is another feature of this minima, which is the fact that these are the least fragile, the least stable among all these minima. What does it mean? It means that if you look at the distribution of the eigenvalues of the Hessian evaluated at this minima, this distribution, well, has a support that is positive, but it is, in fact, touching zero. So these minima are marginally stable. So what is going on here? Well, these are the minima that are the least stable, so the most susceptible to the increase of the signal-to-noise ratio. The first that will lose stability when the signal-to-noise ratio increases. And this will take place with, well, a mechanism that is called Benarus-Baik-Péchet transition, so the BBP transition. Gerard was talking about it before. So there is one single isolated eigenvalue that is popping out from this bulk, from this distribution, and since the bulk was touching zero, as soon as it pops out, this eigenvalue is negative. And there is more than that, because when you have this negative eigenvalue that is popping out, the corresponding eigenvector turns out to be correlated, so pointing in the direction of the signal. So the way we should figure out what's going on here is that this gradient flow is going down from high value of the risk, is approaching these highest minima that are the least stable, and then for enough large signal-to-noise ratio, these least stable minima will lose their stability and point into the direction of the signal itself, even if there is a huge structure of minima underneath. Okay, so in other words, the dynamics is, well, thanks to this analysis of these dynamics, the aging dynamics that the algorithms is performing at this structure of the landscape in terms of this BBP transition, what we can tell is that gradient flow is flying on top of all these minima and finding the signal, even if the structure of the landscape is very much rough. And we think that this might be a very general setting, okay? This turns out to be the case in this Tensor PCA, but we think that it might be also something that is realized in other contexts, in other inference problem. Okay, so that was for this mixed spike tensor model. And so talking about general result, what we obtained here was a way to improve the algorithm, the gradient descent-based algorithm, but that was specific to this model. So another topic I want to touch, and this will be the last for this presentation, is a way, well, a method to make this gradient descent-based method algorithm to be competitive and match the performance of the best known algorithms so far in a more general setting. Okay, this will be the last section. Okay, that's a slide that is recapping what Gerard was explaining very well already. So the setting we are going to work on is the original Tensor PCA problem. So vanilla plane, we have just K and P are the same, just a tensor. We will be typically focusing on K equal to 3, okay, which is the first hard problem that we have at hand. The scaling we define is such that the information theoretic transition will be a signal-to-noise ratio of order 1. And you remember in this large size limit for the problem, with the limit of infinite number of parameters to be estimated, we had that for k equal to 3, we have this infinite band of minima at the equator. But if we consider the finite system size problem, as Gerard was telling you, well, gradient descent and A and P are going to have an algorithmic transition that is growing with this size of the problem with the power k minus 2 divided by 2. And there are algorithms that are doing much better than that. Tensor folding, sum of squared, and homotopy. These are having algorithmic transition at n to k minus 2 divided by 4. And well, the recent result by Moore is telling us that also approximate message passing can match these performances if you use the right trick, the right Kikuchi hierarchy, and generalize it to that situation. You can reach this algorithmic transition. So what is left here, at least in this slide, is the gradient descent. Can gradient descent do as good as the other? That's the question.
What is the computational complexity of those algorithms? Are they more or less the same, or is there any advantage?
It seems, okay. I don't know that much of the details, but I have seen in the homotopy-based methods, so the paper, they are comparing all these methods, all these algorithms, and they're claiming they are the best from all different perspectives, or at least making the balance between algorithmic complexity and time that you need to achieve the performances and everything. Okay, so they say that homotopy is going to be the best among all them. Okay.
And is the motivation for improving gradient descent for this particular problem is also kind of achieving better algorithmic complexity, or is just understanding?
It's mostly understanding. Yes, because I mean, there are, as Gerard was saying, there are a number of arguments that start to say, okay, we cannot do better than that. Okay, that would be like our own way to say why gradient descent cannot do better than that, and linking that to the landscape, that might give a hint on why other cannot do better than that, but I would not go so far for the moment. I mean, that's like a good direction where to go and attack the problem from, okay? All right, so how can we help gradient descent to do better? And of course, we have seen that a lot of the issue come from the rough landscape. So one strategy, the dream, would be to flattening out this landscape. And then we will have only to deal with the entropy problem, and at least not worry about the structure of the landscape. But that would be even slightly better, at least. Okay, what is a strategy to flattening the landscape? What it is used in machine learning is to deal with empirical risk functions that are obtained by averaging of a very large number of data. In that case, the intuition is that the different data are bringing different realization of the noise, and then by adding them up and evaluating the average by means of the central limit theorem, what you're getting is the emergence of this, the emergence of the signal out of the noise, okay? And this is the mechanism, or at least one of the elements that makes gradient descent work in a very good way in the case of these empirical laws that are averaged over a lot of images or of data points. Okay, so what can we learn from this strategy? Because the thing is that in our situation, we are dealing with a problem in which we have only one data point, okay? That's the hard inference problem we have at hand. So we cannot use this strategy. But we can learn the philosophy of this strategy and maybe think that, well, this single data point will bring independent contribution that comes from the noise that will be uncorrelated if we sample the landscape that is coming from that single data point in regions or in positions that are sufficiently far apart, distant enough, okay? So the idea is the one of averaging the information that comes from the empirical risk in different regions of the landscape, and then use this averaged information as a source of a stronger signal that we can follow to let our gradient descent to do better than what it was doing with the standard gradient descent method. So this is the idea, and you see the way I presented it, it doesn't connect with any specific inference problem. We just have to deal with one single risk function that we want to minimize. So I will go further in the presentation of an algorithm that is inspired by this idea, which is this replicated gradient descent, and I will present it in full generality, starting from this general risk function, which I call h, as a function of the parameters to be estimated, the function that we want to minimize. Okay, so the idea is here, what we do, what replicated gradient descent prescribes, is to sample different vectors of the parameters. And this sampling will be uniform in the regions in which you are searching your parameters, so this region omega. Once you have these different vectors, what you evaluate is the center of mass of this cloud of vectors, and you evaluate the averaged gradient descent of your risk function by averaging the gradient descent evaluated at all the different points. What you do then is to use this information, so this averaged gradient descent, to update the position of your center of mass by simple gradient descent prescription. And what you redo at that point is to resample uniformly in the same region omega the new R vectors at the next step, but this time you sample in a way that is conditioned to the fact that the center of mass of this new cloud of minima must be the one evaluated at the previous step. So then you update, and you continue like that. So you have the first cloud, the motion of the center of mass, the second cloud, and the further motion. So what this algorithm is doing is precisely like keeping as uncorrelated as possible, even from one step to another, the region on which you are sampling your landscape. Okay, and then use this uncorrelated information to average out the source of noise and let the signal to emerge. The intuition, of course, is the one that I already have given. Well, the idea is that this averaged gradient will be the sum over the gradient of the different evaluated at the different point, and this gradient will contain a signal part and a noise part, and well, the signal part will go through the average without being changed, but the noise part will acquire a factor 1 over square root of r, which would correspond of having a signal to noise ratio, which is larger, well, acquires a factor square root of r instead. Now, if r is a certain power of the number of parameters to be estimated, at the price of having an algorithm that is slower but only by a power law factor, you will get a signal to noise ratio that will be effectively larger by a power law in n. And this might cover this algorithmic gap between the best performing algorithm and the one that gradient descent was doing. So let's see if this is going to be the case. So this is the application of this strategy to Tensor PCA. There is an additional element that makes that this replicated gradient descent is really good for Tensor PCA, and this is model specific, is the fact that instead of using a finite number of vectors, in this case we can define population averages for the gradient itself, which is even better. And what we can do is to perform these, well, what we can do is rewrite the gradient descent of this infinitely replicated gradient descent algorithm in terms of the position of the center of mass and solve numerically this, well, do the gradient descent numeric realization of this update. So what we obtain if we do that is this result. So you have in this plot the signal to noise, we have in this plot the correlation with the signal that is reached at the end of the dynamics for different problems of different sizes as a function of the signal to noise ratio. You have, so what you see is that when the size goes larger, the crossover from poor performances to higher performances that, of course, goes from small to high signal to noise ratio becomes sharper and sharper for bigger system sizes. And you observe that the curves have a crossing point. And this is because we have rescaled the signal to noise ratio by this factor n to the power 1/4. Of course, we have tried other exponent here for the rescaling, and this is the one that performed the best in terms of giving this crossing point, and which is telling us that the algorithmic transition in the limit of large n is expected to grow in terms of this signal to noise ratio as n to the power of 1/4. And this, for the problem we are at hand, k equal to 3, is nothing but k minus 2 divided by 4. Okay? So this is the algorithmic transition of homotopy and sum of squares and tensor folding, so the best known algorithm so far. And this strategy is letting gradient descent to achieve that.
And how many replicas do you need to do that?
So this is realized for population averages, which you can do that. But we have done numerical implementation of that for finite number of replicas. But if you go to 10, something like that, you already get very good. Of course, one has to do a very accurate analysis of the scaling of these two to get precise answer to your question. But on top of this, which is something I wanted to say anyhow, there is the fact that this is a numerical result, and this result at finite R is also a numerical result, but we have also developed unwavering heuristic argument that derives this scaling for the algorithmic transition, both for this population average case and for the finite R case. And we have obtained that there is a maximum number of R that you need to find this result already, okay? And this maximum number of R scales with the size of your system. 1. All right, I have one last slide. And this last slide is about understanding why replicated gradient descent is failing. So, which is a way of characterizing this well-defined art phase, at least from the point of view of gradient descent. So it's a way of giving one first information about the nature of this hard phase on which all the algorithms are failing. How do we do that? What we do is to plot parametrically the dynamics. This is this replicated gradient descent dynamics, different instances of that for a specific value of the signal to noise ratio and a specific value of the size of the system. And I say parametrically because we plot them not as a function of time, but as a function of the norm of the center of mass and the latitude that the algorithms has reached at the different stages. And you recognize in these trajectories two different regimes. The first one in which this latitude is slowly increasing, and the center of mass is also increasing. And then there is a second regime in which the center of mass is not moving anymore. And the reason is that the center of mass has landed on the sphere. And from this point on, is only the latitude who is changing, either is increasing or is unfortunately decreasing and going back to the equator, the nasty region where you cannot escape from. So this is bad and this is good. Now, why this second regime is performing in this way? We have to find this, the answer to this, of course, in the landscape. It's also because in this second regime, where you see that the gradient descent, where you see that the center of mass is on the sphere, this operation of averaging over a number or a different number of points just becomes a useless operation, because when you condition on the fact that the center of mass is on the sphere, and this point in which you are sampling are on the sphere, you are always sampling the same point. Which means that the second part, the second regime, is just gradient descent. So the advantage that replicated gradient descent achieved was only in this first part. And so what is the important information here is where the center of mass has landed on the sphere. The whole advantage that comes from replicated gradient descent is to let it land in a region in which the simple gradient descent will be able to perform well. And you remember that, well, we have a picture of that, because we have a picture of the structure of the landscape as a function of the different latitudes. And we have a boundary here. Okay? So what we can do is to report this boundary on this axis here. It will be this boundary. And this is separating two different regions. So this axis is representing the signal-to-noise ratio times the latitude that has been reached at the end of the first regime. And well, this is the starting point for the simple gradient descent, the second regime. And depending on where it has landed, whether above or below this region, well, this gives different fate to your algorithm, to your second part, the simple gradient descent, whether this will be able to retrieve the information or not, or be stuck to the origin. And you see that this threshold here is describing what is going on, because the other coordinate here are representing the actual numerical result at the end of the second regime. So we have an understanding of why it is performing good or badly, and precisely what is the meaning of this threshold, because it's telling us that where it has landed, it was smooth here, and therefore gradient descent can go there, can go to a value of the information, or rough, and then it stays stuck on the equator. So I finish with that. There is a slide of conclusion. I will not, repeat the result that I was already showing. Just wanted to throw at you a couple of questions. What I am showing you is how much the landscape can tell you, especially for these gradient descent algorithms, of course, but I was even pushing a little bit forward by saying that maybe this is a way to understand the origin of this well-defined hard phase in which, like, all the algorithms are not performing, cannot perform. And the question is whether maybe we cannot do better, because replicated gradient descent that is already exploiting the information contained in the landscape at best, and well, all the information for our inference problem was already represented in the landscape. This is some possibility or question that we might want to discuss about. Thank you for your attention.